Let's move to sufficiency. Just to remind you, we're trying to come up with a notion relevant information in the data, relevant to our inference task. Okay, so what we came up with is this notion of sufficiency, which is saying that if you have a model, which is, let me do this here. So if you have a model, which is a parametric family of probability distributions for X, the statistic T of X is sufficient for P, or for estimating theta, if the conditional distribution of X given T does not depend on theta. And so what this is saying is that if I have T, basically I can simulate an equivalent data from the distribution without knowing the parameter. And so we can use this, and everything that I can do with X, I can do with T, basically. Right. And then we did an example where we actually used the definition to come up with an argument that in the coin flipping example, the sum of the entry is basically the number of, let's say, ones, where the number of heads is sufficient. So we went through the calculation, calculate this conditional distribution of X given T. This is a discrete example, so everything is easy to work out. And in the end, we ended up with this conditional distribution that says, if I have T, the sum, if I condition of the sum, then the distribution of X given that sum is uniform on all sequences that have the same sum, and this doesn't depend on theta. So this, like, intuitively does not have any information about theta. So I don't need to keep whatever is left in X after I take T, and whatever is left after taking out the sum is the order, basically. So you don't care about the order of the coordinates, or the arrival of the order of the observations. So in the language of statistics, that's the ancillary information. It's an ancillary statistic. So the order is ancillary. We'll see that. So the information that's not relevant to the task of estimating theta. Okay, so this was, and then we ended up, okay, that's where this sort of slides ends. And then there was a next question. Do we have to do it all the time? This, like, go through the definition, and the answer is fortunately no. There's this factorization theorem, which is due to Fisher and Neyman. What it's saying is that if you have a family which is dominated by an underlying measure, basically this means that these guys have densities, so P theta has density low P theta of, let's say, X, if you want, with respect to this mu. So we have these densities, and then the result is saying that if this density can be factorized in this fashion, there are two factors. One depends on theta, and the other one does not depend on theta. So the one that depends on theta only depends on the data through this functional form, like T of X. And if that's the case, then T of X would be sufficient. And also the other way around, if T is sufficient, there is some sort of such factorization. So the proof of the interesting part is like, if this holds, then T is sufficient, is very similar to what we did for the Bernoulli case. So you can go through it exactly the same, except that for P theta X equals X, I have this Bernoulli form, and you plug it in and do the calculation. And you see that in the end, the conditional distribution of X given T is not dependent on theta. So that's the proof. The other way has a one-line proof, which I'm going to skip. You can read this in the discrete case. Basically, the factorization is given by when you try to condition on T, and the pieces sort of come out. This is for the discrete case. In general, it's going to be much more complex, but I'm going to ask you to believe me, or like believe whoever this theorem is due to, that this result hold in general? Okay, is it clear? So we did a quick little example here. For the Bernoulli case, you write down this is the joint density. So the density of basically this vector. And once you simplify, you can see that this can be written as g theta of the sum. So the functional form, the density is a function of theta, and that functional form only depends on sigma of xi, and that h is 1 here. So this is a one-line proof that the summation of the entries is sufficient. Okay. That was where we stopped. Okay. Good. No questions? Here's another example. So suppose that x1 up to xn are IID uniform from 0 to theta. So this is the notation for a uniform distribution. So the densities are, so what does the density of this look like? The uniform distribution of 0 to theta. Who said that? Yeah.
Indicator function.
Yeah, what was your name again?
Raymond.
Raymond, okay. I'm gonna learn at some point, like a very slow learner. Raymond, indicator, so yeah, so let's say indicator of what, sorry?
Of 0 theta.
Yes, indicator and 0 theta, so what is the level? Like,
It's 1. It's 1 and 0 theta, 0 x.
okay, is this correct?
Oh, it needs to divide by theta.
Okay, good. So it's not gonna be 1 because we have to have it sum to 1. So it's gonna be like 1 over theta here, and then 0 elsewhere. At the boundaries, you don't care. Right, that's the density. So it jumps to 1 over theta over 0 to theta. And the area is 1. So this is the PDF, probably density function. So the Wegg measure. So this is what we have here. So that's the formal way of writing 1 over theta, indicator xi and 0 to theta. That's for the ith coordinate. And I have n, so you get the product. So that's the joint density. Right. And so I multiply out. I multiply out 1 over theta, I get 1 over theta to the n. Right. This multiplied out 1 over theta n times, I get 1 over theta. And then there's this part, which is a fancy way of multiplying these indicators. So I have a little sort of fact here. So if you multiply a bunch of indicators, that would be the indicator of the intersection, right? So this is going to be 1 if and only if all the events sort of happen simultaneously. And so this is saying that the product of these indicators is just that all of them are in 0 to theta. So I can break it up into 2 pieces. There's a part that doesn't depend on theta, which is not that relevant to us. So if all the xi's are between 0 to theta, what I have is that the minimum, it's equivalent to saying that the minimum is bigger than 0, maximum is less than theta. Okay. And so I have the product of these 2 indicators. Right? Again, you can think of the product as the intersection. So this event that this is describing is saying that minimum bigger than 0, maximum less than theta, which is equivalent to all of them being between 0 and theta. But this has this nice form that this part now you can think of as, would have been better if I put it on the other side. So this is like 1 over theta n, indicator max xi less than theta, and then indicator min xi. So you can now recognize this as some g theta of max xi, and then this as h of x. So this is a factor. So this is factorized into the product of these 2 terms. One is independent of theta, and the other one that depends on theta only depends on the data through this max of xi. Right. So the factorization here, I'm telling you that maximum of these is like x1 up to xn is sufficient. Okay, very easy proof. So here, for example, the summation is not. So if you take the average, that loses, like you lose information. Actually, we haven't shown that that's not sufficient, but you can guess that if you have the sum, basically, you can't recover the maximum. Now we'll see. Actually, still, there could be something which is sufficient and has less information. We'll get to that. But it turns out in this case, the summation is not informative. It's informative, but doesn't have all the information. Okay. Intuitively, it's clear. So you want the parameter is the end of the boundary. So the max is very informative about it, but the average may not be as informative. Okay. Yeah.
Will there be only one sufficient factor for equality?
That's a very good question. Anyone wants to answer that? Will there be only one sufficient statistic? Yeah, let's go with him first.
You can always just rescale it.
Rescaling. Okay, great. So if I have this 2 times, this would be another sufficient statistic. So sorry, what was your name again? Stephen. Okay. What was your name again?
Dan.
Dan. Okay.
So in this case, the min statistic would be just as informative as the max statistic, right?
The minimum you were saying?
Yeah.
Is it going to be as informative?
It's gonna be this, it's gonna be also sufficient and just as informative.
You're saying like the minimum of xi?
Yeah.
Why would that be?
Because like,
So
it's,
the one part, this part is the interval is 0. So if it was like, I might have agreed with you, sort of, if it was like this.
oh, I see.
Right, but this side, so the minimum is going to be very getting close to 0, let's say. And 0 we know,
Oh, okay, I see.
right? I don't know the top end, right? And in that case, the maximum is, so I can recover the minimum from the maximum. But you're on the right track, so there could be other statistics. Yeah.
I'm not sure if it's true or not, but like just looking at the first quality, is the data itself sufficient?
Great. That's another great point. The data itself is always sufficient. So that's where we're headed. So what does it mean to be minimum sufficient? What have you seen it, or like you predicted like the trajectory of where we're going? So the data itself is sufficient. This is also sufficient. 2 times this is also sufficient. You can see like the pair data itself, and if I sort of let's say I take like x1 and the max. This is also going to be sufficient, for example. Okay, this has some extra information, but it's sufficient. It contains all the information I need, a little bit more, but the data is, sorry?
How would that affect admissibility?
The so we are not talking about admissibility. At this point, there is no discussion of the decision. So what we're talking.
Like, I was wondering how that affect admissibility. If we added more information that we don't need, I guess.
Admissibility is a property of an estimator. So we're not talking about estimators at this point. So I'm not talking. So your estimator, you can have an estimator that depends on the entire data and it's still admissible, right? And the entire data is not compressed enough. It's fine, right? That's a different kind of question. So we'll see. The sufficiency is like at a lower level than decision theory. So whatever we do here preserves the statistical problem. Later, you can like change your loss, admissibility, everything changes, but this information is below that. So it doesn't matter if you change your loss or, so for example, admissibility is like very tied to the loss. You've seen like if you change your loss function, you can sort of make an admissible estimator inadmissible. But this is like more fundamental than that. So if I keep this, I can keep everything in the problem. Later, I can choose my loss, like, hey, so nothing is lost. Okay. And then this is sort of, but we'll see, like sufficiency gets like, we'll see the connection to the like loss and what happens if you incorporate additional information unnecessarily. Sometimes you lose in terms of, it's a good question, but it takes a while to realize that this is a little bit more general, like before we get into the discussion of loss. But keep that in the like backgrounds till we get to the discussion, and you'll see the effect. Okay, so this is also sufficient. The data itself is sufficient. There's another version of the data here which is sufficient, which would be interesting to see. The data itself is like very like an obvious choice, but they can do a little bit of transformation. It's still sufficient, and it's not that clear. Anyone sees relates to the IID nature of the data. Whenever you have IID, you can do some reduction before even you look at this.
Subtract the mean.
Subtract the mean. Is that going to be sufficient? If I subtract the mean, can I recover the mean back? No. So if it's like a you lose information. I'm not sure in this case it's going to be sufficient. You have to prove to me that that's sufficient. It's not obvious. Let's go, because according to the order in which you raise your hand. So what's your name?
Michael,
Michael. Okay.
speaking of order, I'll give it like the order.
Okay. So you got okay. How about you?
Same.
Same.
Other stats.
Great. So we can reorder your data. Okay. So if I give you like x1 up to xn, you can just like say this is the first one, this is the second one. I don't keep the order around. It's just the subset of the values. I'm not going to keep track. So for example, if you observe, in this case, you might observe the first observation would be 1.5, the second 1.4, like 4, 5, 2, I don't know, minus, can be minus 3.8. Okay, so I observe the sequence, but the thing that's sufficient is these values. So it doesn't matter if I observe it in this order or like keep track of it in this order, or as long as I keep all the unique values and then how many times they repeat. So you can destroy the order. And this happens, like this is sufficient for any IID model. We'll get to that. Okay. So this is a pretty dramatic reduction, or like let's say milder level of reduction of information that you can do that holds in more general setting. This is saying I don't care. I just care about like the largest element. Not only the order doesn't matter, like all these values are not important. Only the bigger one. Or order them, keep the last one. The last of the sort of order statistic is important. This is not true for a general model. Okay. Good. Any other questions? Let's see what is next. Okay, next is exactly what we talked about. So the entire data is always sufficient. In the IID case, there's always more reduction. So formally, you can take the order statistic. So if you have a x1 to xn from the data IID, the order of statistics is usually written like this. So I think this is the notation of the book as well. So the minimum value would be x1, and the maximum value would be x subscript in parentheses n. So you put parentheses. So this is the minimum. This is the max. This is the mean. The median would be somewhere in between, and they're like in the middle. And so what we discard is the rank of the data. Okay, what are the ranks? So the rank says which one of the original one had this value. So which one was the minimum? Which one was the maximum? So like the 5th observation was the minimum. Like the 10th observation was the maximum. I don't know. The 2nd observation was the second most largest or smallest. So the ranks are sort of ancillary. You can discard them. You'll keep the order statistic. Okay. Questions? Okay, so now, given this information, there's a natural question. So is there like a smallest sufficient statistic? Right? That's the natural direction of this line of inquiry. So, and it turns out there is a hierarchy among sufficient statistics. Intuitively, we can see, for example, the order statistic has less information than the original data, and like a maximum has less information than the entire order statistic. But we have to formalize what it means to have more info or less, right? So I should have asked you guys, but like, pretend that you didn't see this. So how do we formalize the notion of reduction of info, like losing information or reducing information? Yes.
If you have two statistics, like one can be recovered as a function of the other.
Yes, good, exactly this. But why, like this is a notion of reduction. So why do we why can we view functions as reduction mechanisms? Is there like mathematical reason why? So it goes back to the very definition of the function. If you've seen the functions, the first time in mathematics, there's a definition, right? Anyone remembers what the definition of a function is?
Map.
It's a map, but it's not any map. So there is a little bit of functions. I don't know when, or I can't remember the first time I learned about functions. But the first time you learn about them, they're not just any map, right? So suppose I have like A, B, C, 1, 2, 3, 4, let's say B here. Okay, let's say C. So from this space to the other space, yeah.
I mean, to answer the previous question, it's because like when you apply a function to something, like this is like equivalent to subdividing the domain into equivalence classes.
Subdividing, okay. Okay, yeah, so it gets to the point. Yeah, so I'm gonna get back to that point. But what is the definition of the function? Let me maybe what was your name? Yeah, sorry. Okay, I can hear well. Sorry, what was that? Okay. Every element in the domain gets mapped to one element here. Okay, so what does that mean? Yeah, like what is the alternative? Like what is not a function here? If I oh, okay, good. So if I map A to 2 points here, that's not a function. So everything here in this side has to be mapped to the exactly one point there. But I can have multiple, like multiple points from the domain mapped to the same point in the codomain. Say, okay, so that's the definition of a function. You can't have, so it's like there is some sort of a uniqueness. So every element in the domain has to be mapped uniquely to something on the other side, but two elements in the domain can be mapped to the same element. Okay. So that's, and you can see when this happens, when multiple elements gets mapped to one, there is a loss of information, right? Because if I observe this, I can't distinguish between A and B anymore. Right? That goes back also to the idea of like level sets. So if I look at the level set of the function, so all the points that get level 1, so basically this like, let's say f minus 1 of 1, the set of all the points that get mapped to 1, this is f, this would be A and B. Okay, so this is ambiguous. Again, this discriminate. So when can I discriminate? What would happen if there's no loss of information if it's 1-to-1, yeah, not necessarily bijective, but if it's 1-to-1, then so for example, if I have this is, so this is like loss of information. So this goes to this, for example, this goes to that. And there could be some other points here that are not mapped. So this is bijective, there's not bijective, but like 1-to-1, like injective, right? This is like mathematically called injective. And so this is like no loss information. Um, and then there's equivalence between the statistics if there is a bijection. Okay, so so that's basically the idea. Okay, so we formalize the notion of reduction or being smaller in terms of carrying information by saying that one statistic is a function of the other one. Okay, and they have equivalent information if there's a bijection between the two. So here's a formal definition. So T, so actually this is like not the definition, but the little lemma that inspires the definition. So if T is sufficient for a family, and T can be written as a function of another statistic, almost everywhere P, again, because these are defined almost everywhere, then S is sufficient. Okay, you can try to prove this, but this should be sort of clear, right? If this is sufficient, you can read it as a function of S if you understood the notion that we talked about. There is a reduction that's happening to get to this. So the original one has to be sufficient if this is sufficient, right? So there is some reduction from S to T. So if T is sufficient, the one that is driving it, like, or to drive the T from it should be sufficient. So I'm going to write this relation that T can be written as a function of S almost everywhere. T almost everywhere means almost everywhere under all the T theta. So this is for the measure theory people, almost everywhere. T theta for all theta. So it doesn't matter which theta it is. The set that this is violated is a null set under all of that. So I'm going to write this notation, like this notion, as P is less than or equal to S in this, let's say, man-made inequality. Not man-made, but artificial. So this is not a standard notation. It's like my notation of saying that T has less information than S. It doesn't mean that T is like pointwise less than S. It just means that T is a function of S. And this additional nice measure theoretic sort of nicety also there. So if T is less than or equal to S in this notation, T can be written as F of S also. Okay, so this is an easy consequence of the factorization theorem if you want to prove it, but yeah, but if you understood what I said, it should be evident. Yes.
So you say almost everywhere for like the probability measures. Does that mean that we put like a prior on theta?
No, what I mean is, so what I'm saying is that this is saying T is a function of X, let's say, right? X is a random variable, right? And S is also a function of X, right? And X has a distribution, right? So this inequality, so this side is a random variable, this side is another random variable. Two random variables are equal. It's a little bit problematic, okay? So because they can have like, they can be like not equal on a measure set of measures.
So I should see the math output as like P theta instead of.
That's the thing. So this is like this the family. So this script P is P theta theta in omega. What I'm saying is that this holds under P theta for all P. Does that make sense? Yeah. Yeah.
So, so are you saying that like the set where it fails, or the union over all theta of the set where it fails for each theta, like is measure zero for each?
Not the union, yeah, because the theta could be
They could be different failure sets for each theta, or does it need to be like a common null failure?
I don't think you need a common null set. It's just that under each theta, it is a set of measure zero. It doesn't have to be I don't think it needs to be. Yeah, but I'm gonna not worry too much about this. Again, this is the measure theoretic nicety. It's not a statistical issue. So the statistical ideas I'm gonna focus on. But you'll see if you really care, you can think about it. I don't think it's needed that it's a common set. It's better if it's a common set, but it could fail, but I don't think it's needed to be the same set. Okay, any other questions? Yes.
The whole reason we are doing this is to reduce the size of information we are storing.
Yes.
But if it is a one-to-one mapping, then what exactly is getting reduced?
Sort of nothing. So that's this. So let's say if P is sufficient, if I form P squared, there's a loss of information. Okay, this is not a one-to-one map. I reduce like if assuming that like P can take positive or negative values, I use the sign. So if this P is sufficient, and let's say supported on negative infinity to infinity, this is not necessarily sufficient. So I can't say this. Assuming again there's some like caveat here that the underlying measure is such that T has like distribution like positive and negative. If you want to really, there is a sign to be recovered. So if this is sufficient, then I can definitely recover T. Sorry, not recover T. Then T is sufficient. Okay, because this can be written as a function of that. Okay. If T is sufficient, T to the character is almost sufficient, and vice versa, because I can recover one from the other. So there's no loss of information. Okay.
It was to reduce the amount of information.
Right.
In previous examples, instead of storing entire data, we are just storing one part.
1 point. Yeah, that's one real number, let's say, instead of n real numbers. Yes.
But like, what's the point in doing this T equal to F of S if both of them are going to be?
It is not. So these are equivalent from our perspective. So each one is okay. If it's a one-to-one map, we're saying that they have the same information. They're equivalent, like statistically. It's not information theoretically. For example, information theoretically, storing like 2 bits is different than 1 bit. Okay, I don't care about that part. Let's not worry about that, right? A statistic. I'm talking about statistical information, not it's an interesting question. But, for example, yeah. We'll see if there's a bijection from like x1, x2 to some function of x1 and x2, then they have the same equivalent information for us in some cases. But yeah, the idea is that this allows me to say what is smaller and what is like equivalent. That's so I can decide like what is minimal. Okay, because I can always do this, but I'm not going to say that they're different statistics from our perspective, like they're both equivalent. Okay. But there is a reduction here going on. So I want to recognize this kind of thing, not this kind of thing. Okay.
Are the same.
Statistically, yes. Yes, for us, statistically, it doesn't matter which one. Yeah, because I can recover one from the other. Okay. Right?
Then why are we doing that?
No, we're not doing so. Let's say if I manage to show that T squared, for example, is more informative than T, not more informative, as informative as T, I can store this, I lose some information, but I'm okay with that. Maybe I can reduce this further. Right? It's not only the compression issue, right? It's not only the issue of compression. It's what so for example, there's a natural idea here, right? There's a natural idea that this is smaller than the original data, right? But the smaller doesn't mean that this has one coordinate, the other one has more. It's the notion that this has less information is in the idea of sufficiency for us. Okay, it could be like still like a n-dimensional vector, but has less information than the original one. For example, this example is this. Okay? So the ordinate statistic, the content is n-dimensional still, sort of, but there is a loss of information. There's no order. You can still say there is some sort of like it's still n numbers you're storing, still n numbers, but there is a loss of information, right? And that loss of information is okay for us. Not sure if I'm answering the question, but this formalizes what it means to be smaller. Okay. That's what it means for us to be smaller. There is a mapping that maps us down by a function that I can't reverse, like invert. Okay, other questions? Let's see if this is recorded. Okay. Okay, this is a repeat of what I said. So that notation is not standard, but it means there exists a function such that p can be written as a function of s. So we want and obtain a statistic which is sufficient and achieves the greatest reduction. So that's the definition of a minimal sufficient statistic. P is sufficient, and for any other sufficient statistic s, t is less than or equal to s in this notation. Okay, so what this means is that for any other sufficient statistic, I can write t as a function of s. Okay, you give me any sufficient statistic, I can find a function. So t is like here. You pick s here, I can find a function that maps it down to t. There's another s prime here, which is sufficient, another function here maps it down to this. There's another sufficient statistic, I can find a function that maps it down. So no matter what sufficient statistic you pick, I can find a function that gives me t. So this means that it's at the bottom of the hierarchy. It could be like the notion of uniqueness is up to bijection. So there could be some other t prime here that has the same property. So I can find mappings from this to this. Then you can argue that there should be a bijection between t and t prime. Okay. Because this is sufficient, so there is a mapping from this, and this is also sufficient, so there's a mapping. So if you have two minimal sufficient statistic, because they're both sufficient, and because of this fact, there should be a mapping in both directions. So there is a uniqueness up to is bijection.
When you say that they have the same properties and like expectation differences, what do you mean by they have the same properties?
When did I say they have the same property means like these two. If I have t prime, which is minimum sufficient, it's sufficient and this holds. So suppose so let's say this is minimal. This is also minimal sufficient. So what I'm saying is this has these two properties. This also has these two properties. Okay. Because t prime has these two properties, t prime is sufficient, right? And because t, I can do like put t prime here, right? So t would be less than or equal to t prime. So there is this function here that maps t prime back to this. In the other direction, because t prime is minimal sufficient and t also is sufficient. Okay, I can say that this is t prime is sufficient and t prime is less than, I can take t here. And so there should be a mapping this way. Just think a little bit about this. What I'm just saying is if there are two minimal sufficient statistics, by this definition, there should be a bijection between one you can write as the function of the other and vice versa because of these two properties. That's like a minor point. We don't have to worry too much about this. That's the definition. Okay, the definition is good. Okay. Okay, let's now try to see if we can find a minimal sufficient statistic. It's sort of unique, sort of. So they exist under mild conditions. They're essentially unique modular bijections. That's what I mentioned. So let's see some examples which are going to be helpful. X1 up to xn are IID from p theta, that's the density. And the density has this form. So there is this function f, which doesn't depend on theta, and then I shift it around. Okay, so these are called location families. So you have like a base function f, for example, and then every member of the family is obtained by shifting this around. So one could be like this. The other one is like that. This is p theta prime, p theta. So this operation, I hope everyone understands that this just moves things around, like just shifts the function. This is called a location family because the parameter is sort of, the meaning is the location of something. And this is the general form that I'm going to consider. This C is the normalizing constant. Alpha is a measure of the spread. So whether this looks like this or looks like this, that's beta. And then the alpha sort of is like the class. Alpha equal to 2 would give you the Gaussian case. Alpha equal 1 gives you the Laplace or double exponential case. So in the what we're going to see is that in the case of alpha equal to 2, the sum or the average is minimal sufficient. Okay. For example, if you have a location family, Gaussian location family with known variance here, assuming that the beta is fixed, alpha is also fixed. The only parameter is theta. So in that family, with alpha equal to 2, Gaussian location family or normal location family, first by factorization, it's easy to see that this is minimal sufficient. You can see that if I normalize it by 1 over n, it doesn't matter. It's a bijection. There's a bijection between the mean and the sum, so it doesn't matter if I say the sum is minimal sufficient or the average is minimal sufficient. This follows by factorization theorem, okay, which we are not showing. It's easy to show. Maybe you show it in your homework problems. But later we'll see that this is also minimal in this case. For the Laplace case, we know that the order statistic is sufficient. We just argued that because this is an example of an IID case. What we'll see later is that no further reduction is possible. So the order statistic is minimal sufficient. It might be a surprise, but just ending this from 2 to 1 makes the family a lot more informative. That's sort of why the math of the problem becomes more informative. If you observe in samples from a Laplace location family, there's a lot more information than a Gaussian, which is fairly, I would say, like a little bit deep, but you'll see. Hopefully by the end you get a feel for what is going on. Good. It's just not, we're not proving it, just advertising the results to see later. Okay. Sufficiency should be easy to show. We'll see the minimal part. So what I'm going to try to do is try to build some machinery to try to show this. You're going to sort of use this abbreviation, which again is not a standard, it's just my own abbreviation, DCS, dominated with densities having common support. That's going to be the family of probability models that we're going to consider. So they're dominated, which means that there is this underlying measure, so the factorization theorem holds. And the common support means that the densities have the same support. So I can pause here and ask you what the support is. I'm not going to spend too much time, but let's just see if people are comfortable. What is the support of a density or a distribution? Who runs first? Okay, maybe you go and then, yeah.
So it's the
Steven.
closure of the set of points where density is positive.
Closure of the set of points where the density is positive. Okay. And support of, it's a property of the distribution, but you can define it in terms of the density. So what was your?
The possible realizations of a random variable.
The possible realizations of a random variable. And the set, let's say. Possible. So in this course, both are okay. So they have the same meaning. This has a little bit more sort of math in it, so the closure. But the idea is, I'm going to go with again. I'm going to ask your name later to make sure. But so I'm going to go with that definition first. So px. So if you have a random variable, okay, the set. If you can find an event such that the probability of belonging to the event is 1, sometimes people say that X is concentrated on A. And then the smallest such event is the supported distribution. I can't squeeze it further. It's like the smallest, maybe closed set A such that that happens. Okay. If you have a density, this would be sort of equivalent, I believe, to what Stephen said, px bigger than 0, the closure, okay, closure of the set of, at least for the things that are like, with respect to the weight measure, that's far like, where closure means like something. So for example, just for us, it doesn't matter the the rough definition is good enough. So for example, the uniform distribution that we had here, what is this? What is the support of this distribution? 0 to theta, right? And so this family doesn't have the property of having common support. They don't have that property because the support depends on theta. So the support of, let's say, p theta here is 0 to theta, and so it depends on theta. So I'm ruling this case, right? But for example, the case where we have this Gaussian normal family, let's say. So p theta is normal theta and 1. So what is the support of p theta here? The real. So this has a support that doesn't depend on theta. So that has the common support property that I'm looking for. So I don't want the support to depend on the parameter. So this case is ruled out. This case is what we care about. You can like work around this case, but let's focus on this so you can figure out what things are, how things are in this case. But you're gonna work with a simpler case. So if the support is common, I can just work on that common support. So all the densities would be positive. So say support of p theta. I can work on this set on which the densities are all, I can assume that they're strictly positive. Okay. There is some sort of things about if you really want to like bother yourself with measure theory, these are not defined everywhere. So you have to like be some sort of an essential thing, but let's not worry about that. Okay. Good. Okay, so we're gonna work with this dominated densities with common support. So what I want to show, basically, that's what the goal is, to show that the likelihood ratio or the likelihood function essentially is minimal sufficient. Okay, that's the end result. So if I take, if you remember this p theta of x, if I evaluate x, looking at it as a function of theta, so this thing is the likelihood function. These are the densities. I fix x and look at this as a function of theta. This is the likelihood. Sort of the shape of this up to a factor is minimal sufficient. Or if you want to get rid of the factor, I can pin down one of the parameters here and then divide this by that. So this is now a constant, like a variable, random variable constant as a function of theta. This is going to be the likelihood ratio function or process. This would be minimal sufficient. Okay, that's the whole point. So what we're saying is like this entire function, you can view it as a statistic, that the statistic is minimal sufficient. Okay, there's no reason why like a single number should be, there's a function here. And the easiest way to think about it is as the case where the parameter space is finite. Okay. If the parameter space is finite, basically what I'm saying is that you form this vector. So the parameter space, let's say, has 3 parameters. This function is just going to take 3 values, the likelihood function. The x is fixed, right? P theta 2. Well, let's do 4, for example. There's a theta 0. theta 1, theta 2, theta 3. I have these three. These are going to be random variables, right? So once I fix my x here, and the thetas are fixed, these are known numbers. So this is one random variable, it's another random variable, another one. And as a function, you can represent the likelihood function as a vector. There's another one, which is e theta 0 here. So this vector is my likelihood function here. The function can be represented by a vector because the domain is finite, and then I divide everything by p theta. This is going to be 1. I can drop it, so I don't care about that one. So what we're saying is this vector is going to be minimal sufficient, and you can see that like if you understood what I mean, it doesn't matter that the dimension is growing or it's big. That's not the point here. The information is what's smaller than the original one, probably. Okay, so it's expanding the dimension basically. Maybe like X is univariate, but this like has maybe 4 elements. Okay, so you say, okay, it has 4 elements, but so this is bigger. No, because we're talking about sufficiency in the sense that any sufficient statistic, for any sufficient statistic, I can find a function that I can reduce it to this. That's sort of the idea. Okay, in order to show that something like this is sufficient, we have to show that, sorry, minimal sufficient, we have to show that this is sufficient, and also any other sufficient statistic, I can find a function that sort of this property, right? For any other sufficient statistic, this is smaller, so I can be able to, I should be able to write any sufficient statistic as a function of, so if I need this one as a function of any sufficient statistic, that's what I have to do. So to show that this is sufficient is sort of easy. That follows from the factorization theorem. You show that each one of them is sufficient. Then you concatenate them, it's going to be sufficient. Oh, sorry, that's not the other way around. To show that any sufficient statistic, so each one, to show that this is a function of any sufficient statistic is easy. To show that sufficient is not easy. I'm going to correct myself. So it's easy to show that this is a function of any sufficient statistic. If you write down, we'll see this. If you write down the factorization theorem for a general sufficient statistic, by the factorization theorem, you see that this is a function of that sufficient statistic. This is also going to be the same, and so on. So, however many of these you like concatenate, they're going to be all functions of like a generic sufficient statistic that you want. But I just have to concatenate enough so that this becomes sufficient. Okay, and that would happen if I concatenate everything. So that's the difficult part, to show that this is sufficient. That's the plan. Okay, to show that this is sufficient, you have to, like minimal sufficient, you have to do 2 things. One is that this can be written as a function of the sufficient statistic. That part is easy. To show that this itself is sufficient, we have to make sure that we have included everything. This is a very nice result. Like it takes a while to understand, but it captures the like importance of likelihood. Okay. Likelihood is the minimal thing that you want to keep. Okay, good. Sort of questions.
How did you show that it's minimal?
I haven't. It's going to take a while. It's just the plan, right? So what let me show you the details. We can come back. It's just how we try to. So to prove it, let's like introduce some notation. So fix some theta in omega. I'm going to define this likelihood ratio. So for any given theta, this gives me a statistic. Okay, this is a function of x for any fixed theta. So that's a random variable. I'm going to write it as L theta, keeping up with the notation that we just dropped x from. This is a statistic. Fixed theta naught and another theta. This is a function. It's like t of x, right? And I'm going to call this L theta. And this is the lemma in the DCS family. the following two are equivalent. U is sufficient for P. And L theta is less than or equal to U for all theta. Okay, so if this holds, then this holds, this holds, this. BC is found, we fails, then A still implies B, but not necessarily vice versa. So this is what I want to show. So suppose U is sufficient. So A holds. Or let's say A implies B, let's say. U is sufficient. So by factorization theorem, I can write P theta of X, let's say capital X if you want, as G theta of U of X, right? U is a function of X, H of X, right? And I can work on the common support so that this is positive, so I don't have like almost surely, so that I don't have to worry about dividing by not with 0. So P theta naught of X, this holds for all theta, so this is going to be true. Right. Just have to do this, and then you divide. So L theta of X is P theta of X divided by P theta naught of X. So you get G theta of U of X, and then G theta naught of U of X. Here, theta is fixed, so this is some function. Let's call it F theta. It depends on both, but it's a function of U of X. Okay, I've shown that this guy as a statistic is a function of U of X. Okay, so this property holds. And this holds for all theta separately. Okay. Fixed theta, this happens. Right. So the fact that these likelihood ratios are a function of any sufficient statistic is a direct consequence of factorization theorem. So this part sort of is from the DCS idea that I can like restrict myself to that without losing general. Okay.
So the ECS make sure that the denominator not become 0 is that.
Yes, I don't want like if the two have different supports, it could be that I'm dividing like over a reason this has positive mass, this has 0, then I have to worry about infinity. If you allow infinity, you can still do things. We'll see maybe an example. Yeah, we'll see an example when this doesn't happen. But yeah, that's basically to avoid worrying about those cases. There we have like infinite information. So if you have like, we'll see, like if you have like intuitively, statistically, if a distribution has like a support here and another one has support here, and you observe something here, you can rule out this like with confidence, right? There's infinite information in favor of this rather than this. So that's okay. Like statistically, it's fine. Just mathematically, we'll see that. Okay. Statistically, it's good to have disjoint supports. Like if that's the case, like all of the P thetas have disjoint support, then one observation is enough to determine exactly what happens. Statistics is like happens if they have like common support, basically. Otherwise, like there's no statistic, like deterministic, everything's perfectly fine. Yeah.
So it seems we're using the fact that like H in these factorizations is the same H. How do we know that is the case?
So this I can fix an H. That's the factorization theorem. So I can write the densities in this fashion where there is a single H. This is part of the factorization theorem.
The factorization theorem gives you a fixed H and then G is very.
Yes. Yeah. Factorization theorem says there is an H, there is a G, such that this holds like for almost all X and all theta. Right? That's any other questions? So this is one direction. The other one is actually have a proof. Do you want to prove the other way? Let me leave it to you to prove. So you have to reverse this idea. So start from this, go back to that, and you recover the factorization. To prove that, just reverse these steps. So we have this. There's for any theta, you have some function. You revert it, like invert the steps, and you prove that B implies A. Okay, yeah.
So to show this direction, you also have to show that L is sufficient.
L is what?
L is sufficient. But I don't see that one.
To show what direction?
To show B from A. So
No, I'm not saying in B, I'm not saying L is sufficient. You're talking about this same direction that you're discussing,
Yeah,
right? A implies B. So B doesn't say that L theta is sufficient.
So by definition, if L theta is smaller than U, then L theta itself has to be sufficient.
That's the conclusion of this result. So what you stated, once I show this, it follows that, so it's not going to be, so we'll get to this, but the way I wrote this, there is no sufficiency here, right? What I'm saying is that if U is sufficient, this holds. If this holds, U is sufficient. I'm not claiming that L theta is sufficient. Right? So what you're saying is going to be on the next slide. Okay. So if you believe this, then let's say B implies A. I can form a statistic composed of these that satisfy this. How? I can just concatenate all the L thetas. So if let's say I have, what I'm saying is, so put like L, which is L theta for all theta. This is like saying L theta 1, L theta 2, L theta 3. Let's say we have just this case, right? Theta 0, theta 1, theta 2, theta 3. So actually, let's say, okay, L 0. Yeah, okay. Yeah, so like theta is, omega is theta 0. Theta 1, theta 2, theta 3. So I get L theta 1, L theta 2, L theta 3. I concatenate everything. So now I know that L theta 1 is less than or equal to this guy, right? L theta 1, L theta 2, L theta 3. Because I can write this as a function of this, like projection onto the first coordinate. The second one, I can do that as well for the same thing, right? So you see that this satisfies all these conditions, right? So this satisfies all these guys simultaneously. So this has to be sufficient as well, right? So the entire, so each individual coordinate doesn't satisfy it, but if I concatenate them, I can write each one of them as a function of the entire thing. So now this thing in place of U satisfies B, so it has to be sufficient. Okay, so that's the slide basically. Like a little bit, so we form this like vector or like, if you want, function that contains all of these L thetas, and then we know that like if R is a function, is R is a function of U and S is a function of U, then R and S is a function of U, right? Which is concatenate, and that's the little step that I did. So from that, we conclude that basically this step, I can replace it with saying that this is another way of saying it. So this is equivalent to saying that this capital L is less than or equal to U. What I'm saying is that I can replace this with L theta, theta omega is less. This is another way of arguing it. So this is equivalent to saying that the entire function is less than or equal to U because of this fact. And now I can just take U to be this. So this itself is a function of itself, so it's going to be sufficient. But the argument that I did above is good enough. Or you can like write it like that. So that's another way of writing it. U is sufficient if this entire likelihood is less than or equal to U. Right? And if you look at this closely, this is the definition of minimal sufficiency. So if you take this to be take U to be L, from this part we get that L itself is sufficient, and also this is saying that if U is sufficient, then L is a function of U for all U, so this L has to be minimal sufficient. So this statement both shows sufficiency of L and also minimal sufficiency of L. It seems a little bit circular, but if you think about it. Okay, so this upgraded, not upgraded, but just the same as this. So you just replace it. And then you look at this hard enough, you can convince yourself that this means that L is itself the minimal sufficient statistic.
First, to
Yes.
show L is the minimum, so you will need every sufficiency statistical L should be a function of any sufficiency, but U is on one, right?
So let's say I want to prove, so if you believe the lemma that I wrote, right?
Yeah.
Do you like, are you okay with this lemma?
Oh, yeah, the lemma is.
Okay, so now I'm gonna apply the lemma. Take U to be, so what is your question?
To show that how to show L is a minimum sufficient.
Okay, so,
Yeah, because U is only one sufficient, you have to show that L is a function of any sufficiency.
right, so pick a sufficient statistic. Pick a sufficient statistic, U, right? Then U satisfies A, then A implies B. So L is a function of U. Okay.
Oh, U is self is
No, this is saying any sufficient statistic of take, then the second one holds, right? And because the second one holds, and I can apply the second one with U being L, that in that case, which is implying, so B with U being equal L implies that L, implies A, which is saying that L is sufficient. Okay, so B implies A gives you the fact that L is sufficient. A implies B shows that it's minimal, so it's minimal sufficient. Okay, you just have to go through it and think a little bit about this. Okay, it's a little bit, it looks like cheating, but we're not cheating. Okay, it's just an interesting fact. This proof is going to be fine if theta is finite. If you really want to bother yourself in the case where omega is infinite, you have to worry about almost everywhere P. So in each one of them, there is some sort of an almost everywhere P. And so you concatenate these things together. Like there are infinitely many things that could go wrong. So then you would worry. Okay, if things are finite, it's fine. So going from this to this is okay. If things are infinite, then you have to worry about all these things. We're not going to worry too much about this. Well, I'm going to give you some examples, like results, which are valid, and you can get around this somehow. But this conveys the main point. Okay, if you understand it in the finite case, that's good enough for me. Okay, finite parameter space. Okay, I'm going to post these slides. Look at them. Think about just this two lemmas. You should be able to argue that for yourself, and then that should give you the fact that L is sufficient and also a function of any sufficient statistic, so L is minimal. So the likelihood is minimal sufficient. That's the end of the story. So we have shown that this is minimal sufficient. This is just going through the same argument that I did, a little bit more, the more variables action. Okay. Questions? Okay, thank you guys. See you next time.
Yeah. So